Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over reversible reactions and dynamic equilibrium. So let's get into this. So I'm going to introduce this topic with an example. So here we have a reversible reaction. Here we have carbon monoxide reacting with water at a temperature of 870 degrees Celsius, and that's going to form carbon dioxide gas with hydrogen gas. And so as you can see with the double arrow here, this is a reversible reaction. And so what that means is uh, as these two are colliding together to form products going in this direction, these two products can then collide together later and reform the reactants. So as these are colliding together in uh, in a container, then forming products, then the products can collide together to reform reactants, and so it goes back and forth. So in this example, you can imagine we have 1 mole of carbon monoxide added together with 1 mole of water vapor together in a 1 liter container. And then you want to ask yourself, what is happening from the very beginning, right? So if you imagine that at the start, we're just adding 1 mole of each of the gases into our 1 liter container. Nothing happens right away, right? So we put the gases into the container, and at that particular instant, no reactions going on. So it's 100% just reactant molecules. So as we said in previous videos, that in order for a reaction to go, they have to collide. The reactants have to collide together with the right amount of energy and with the right orientation. So before any collisions occur, any reactions, we have 1 mole of just reactants. So what's going to happen over time? So as time goes on, the reactant molecules, the carbon monoxide and the water vapor molecules, they're going to collide with each other. And some of those are going to be successful collisions, meaning they're going to form product. So as time goes on, more and more product is going to form. Now, in the beginning, you're just going to have a little bit of product. So these molecules are bouncing around. So they're not likely going to collide with each other in the beginning because you've got so much of this compared to this. So in the beginning, you're going to form a little bit of this. And so you're not going to have much of a reverse reaction. But at some point, you're going to get collisions between these two, and some of them are going to react to reform water and carbon monoxide. So the rate of the reverse reaction is going to speed up. So in the beginning, when all you have are carbon monoxide and water, the forward reaction is the only reaction going on, right? Because these are the only molecules you have, the only substances you have in the container. But as you go forward and you start to form products, these products are then going to reform reactants. And I just accidentally erased my 2 here. So these two are going to start to collide with each other, and they're going to reform the reactants. And so you're going to start to get the reverse reaction starting to speed up. So the rate of the forward reaction is much higher than the rate of the reverse reaction. In the very beginning, it's just this way. So the rate of the reverse reaction is 0 because we don't have any product. As soon as you start to make product, some of these are going to start to react and reform the reactants. So in the beginning, you're going to have a much faster forward reaction compared to a much slower reverse reaction. But think about what's happening over time. As these react to form products, you're going to decrease the amount of reactant. So you're going to get fewer and fewer of these, which means that if you get fewer of these, you're going to get fewer and fewer collisions between the carbon monoxide and water. And that's going to slow down the rate of the reaction. Remember, the rate of the reaction is dependent on concentration. So over time, the concentration of your reactants are going to go down, thus slowing down the forward rate. But over time, you're going to get more and more product, so the concentration of products are going to increase over time. And as that happens, the reverse reaction is going to speed up because you're going to increase the amount of products. Well, what's going to happen eventually? Well, the rate of the forward reaction is going to go down. The rate of the reverse reaction is going to go up until the rates are equal. So now the rates are equal. And so at that point, you're going to have an equal amount of products being formed. At the same time, you're going to have the same number of reactants being formed as well. So at that point, you're at what is called an equilibrium. Now, it's called a dynamic equilibrium because, well, one, it's not an equilibrium. Equal doesn't refer to the reactants and products, the amounts of those being equal. You don't have an equal amount of products and reactants. That's not what the equilibrium is referring to. The equilibrium is referring to the equality of the rates, the forward rate and the reverse rate. So that's where the equilibrium comes in. And it's called dynamic because it's not static in the sense that nothing is happening. It's dynamic in the sense you still have stuff going on. You still have the rate of this forward reaction converting the reactants into products. At the same time, you still have the products forming reactants. So there's excuse me. Sorry about that. So you're going to have you have a dynamic equilibrium because you still have the forward rate going on and the reverse rate going on at the same time, but the rates are equal. So it's not like nothing's happening at this point and everything shuts off. No, there's still things going on. That's why it's called a dynamic. It's dynamic equilibrium. So here I have a couple of kind of graphs to show you that will kind of hopefully make those visual learners see what's going on. But we all kind of learn in some way from visuals anyway. So this will help everyone, I think. So here we have this graph here showing reaction rates versus time. So you'll see that at time 0, we'll mark this off as 0. At time 0, you have the reverse reaction is 0, right? There's no rate of the reverse reaction because we don't have any products. The rate of the forward reaction is up here at its highest point. So at the very beginning, we have a very high rate of the forward reaction. But what happens over time? Over time, the concentration of the reactants decreases because we're starting to form product. So we form product. So what happens to the rate as the concentration of the reactants decreases going this way, right? So we're going to decrease the concentration of the reactants. So the rate is going to decrease over time. But as we form more products, we could see the rate of the reverse reaction start to increase from 0. So now the rate is going up and it's going up. So as more product is being formed, the rate increases. So the rate is increasing. Here's the reaction rate. So the rate is increasing for the reverse reaction, and the rate is decreasing for the forward reaction until when? Until they equal each other. So the rate of the forward reaction is equal to the rate of the reverse. So you can see that the rates of the forward and reverse reaction meet. And at this point here, we've reached dynamic equilibrium since both rates are now equal. They've reached the same point. If I can draw a dotted line here. So whatever that rate is, that's the equilibrium rate for both. So the rate of the forward is equal to the rate of the reverse. You can also see it from this diagram here, where instead of looking at reaction rates versus time, you can look at concentrations versus time. So just as I said before, let me fix this. This is not quite what it should be. There we go. And we'll mark this as a 0 point here. So you'll see here again, at time 0, we start with all reactants. So we have this amount of reactants, and we have 0 products for concentration. So at that time 0, no reactions have occurred. And so now you can see once the reaction time starts, you see the reactant concentration. So this is concentration. So the concentration of reactants is going to decrease as the concentration of products increase over time. So here the concentration of products starts to increase. And what happens to the reaction rate of the reverse reaction? It starts to increase as well. The reactants, the concentration of reactants decreases and decreases. What happens to the rate of the forward reaction? It goes down, right? And so you'll notice here that the reactant concentrations are going to decrease until it plateaus, right? And there's no more change in the concentration of reactants. At the same time, the products are going to increase and increase and increase until it comes to a time where it plateaus, and then the product concentrations stay the same. They are constant. And at this point here, where both concentrations of reactants and products do not change, they're constant, that is where dynamic equilibrium occurs. So again, we're at dynamic equilibrium at this point. Now, the thing I want to point out and stress is that dynamic equilibrium, when you reach dynamic equilibrium, that is referring to the fact that the rates of the forward reaction are equal to the rate of the reverse reaction. These are equal. The rates are equal, not the concentrations. The concentrations might be equal, but most likely than not, the reactants and product concentrations are not going to be equal. So, but what we do know is that at dynamic equilibrium, the concentrations do not change. So they reach a steady state, if you will. So they're flatlined here. And so that is dynamic equilibrium. That's what's going on with dynamic equilibrium. So an analogy might be something along the lines of, say, if you're going skiing at a resort, right? At the time that the ski resort opens, there's no one there, right? So what happens? As soon as the door is open, you get people coming in renting skis at the ski resort, right? So at the very beginning, you just have people coming in from the outside, renting skis. So no one is coming back and returning their skis that they rented because no one's there skiing yet. So at the very beginning, you just have people coming in renting skis. So you got a whole lot of people. The rate of ski rentals is high, right? So you have a high rate of people renting skis and going skiing. So as the day goes on, though, you get to maybe midday, people start to leave. Okay, they maybe after a couple of hours, people are done skiing, they're tired, then they return their skis. So then the rate of people renting skis is going to be really high in the beginning, and at the beginning, people returning skis is going to be zero because no one's there to return skis. But as people are skiing, some people are going to get tired, they're going to have to leave, and so they start to return their skis. So the rate of people returning skis is going to go up, right? And as more and more people are skiing, then the rate of people returning skis is going to increase. And as the day goes on, people who are coming in to ski, that's going to go down as the day goes on. And then as it gets closer and closer to the evening, then more and more people are going to return their skis as people are skiing, as coming in to rent skis, because the day's getting to the end. Who's going to go to the ski resort to ski towards the end of the day when it's about to close, right? So at about closing time, you're going to have a much higher rate of people returning their skis as people coming in to actually rent skis. So that's kind of an analogy to help you understand how this dynamic equilibrium works, because at some point during the day, the rate of people returning skis is going to be equal to the rate of people coming in to rent skis. So you get that dynamic equilibrium. So that might be a helpful analogy to see what's going on, to understand what's going on at the molecular level for reactions. Okay, so at this point, this is dynamic equilibrium, and so we're going to continue with the next part. Okay, let's talk about equilibrium constants. So we've talked about equilibrium and how the dynamic equilibrium is where the reverse reaction, the rate of the reverse reaction is equal to the rate of the forward reaction. Okay, but those equilibriums can be favored towards the products or favored towards reactants. What do I mean by that? What I mean is that when you reach equilibrium, right, you might end up with more products than reactants. So maybe most of your reactants gets converted into products, and you end up with a bunch of product and a little bit of reactant at equilibrium. So, but still the equilibrium is still there. The rates are the same, but it's such that the rate of the forward reaction is producing more product compared to that of the reverse reaction forming reactant. So in that case, you'll have your equilibrium is favoring products. That just means that you're going to have more product formed at equilibrium than reactant you have left over. So an example of that would be this reaction here. So SO2 gas reacts with NO2 gas to form SO3 gas and NO gas. So here you can see that there's an equilibrium arrow here, but you can see that the forward reaction is much stronger in this case, is going to form more product. So this longer forward arrow is indicating that at equilibrium, you've got a lot more product being formed than reactant. So again, you still have that dynamic equilibrium, right? Product is being formed and reactant is being formed, but the equilibrium is favoring the formation of products more than that of reactants. So when you reach equilibrium, you're going to have a lot more of this in solution than this. Or in your container, you're going to have a lot more of product particles bouncing around than your reactant particles. Or you could have the other extreme where the reaction favors reactants, right? So in this case, when you reach equilibrium, only a small amount of the product is formed versus reactants. So you still have a lot more reactants left at equilibrium. So you have the reverse reaction being favored over the forward reaction at equilibrium. So more of this is going to be at equilibrium than this. So you can identify this with the arrows because now the forward arrow is much smaller than the reverse arrow, indicating that the reactant side is favored. So some equilibriums are going to favor products, some are going to favor reactants. So the extent to which a reversible reaction is going to proceed toward products before reaching equilibrium can be described with an equilibrium constant. So which side is going to be favored can be described with an equilibrium constant. Now, how do you get the equilibrium constant? So here is a generic equation. Instead of using NO2 and N2 and oxygen and all that, I'm using letters. So here you have A plus B plus whatever other reactants might be there is in equilibrium with products E, F, and whatever other products. So you can have multiple different products. You have 3, 4, 2, 1. So here's my generic equation. And so to write your equilibrium constant expression is basically it's products over reactants. So concentration of products over concentration of reactants. That's the general way of putting it. But the specific way of putting it is that whatever products you have, you're going to take the concentration of those products raised to the power of their coefficients. So you'll see here in my equation here, I have capital letter that represents the substance, the reactant, and the little letter represents the coefficient, the 1, 2, 3, whatever the number is. So the little letters A, B, E, F, G, and so on, these are your coefficients. So for your K expression, your equilibrium constant expression, there's two ways of expressing it. There's either concentration or pressure. So if you do the expression in concentration, then what you do is you take the concentration of your products and you multiply them together, and they're raised to the power of their coefficient. So here I have product E with an E coefficient. So it's going to be the concentration of E, whatever that concentration is, raised to the power of its E coefficient, little e. Then I'm going to multiply that by the concentration of next product F. So multiplied by the concentration of F raised to the power of little f coefficient. So here's the power of F and so on. If I had G, then I would multiply by concentration of substance G raised to the power of little g and so on. So whatever products you have, you take the concentration of them, raise them up to the power of their coefficient, and they're multiplied together. Then on the bottom, you're going to divide by the concentration of the reactants. So here I have reactant A, so I'm going to divide, I'm going to put that on the bottom. So concentration of A raised to the A power, its coefficient, multiplied by next reactant, so the concentration of B, raised to little b power. And then if I add C, that would be multiplied by the concentration of C raised to the C power, and so on. So that is how you get your equilibrium constant expression. So this would be in terms of concentration if you have concentrations. But if you have pressures, like, if you have gases, gases can be measured in pressure. So you might have atmospheres or millimeters of mercury or whatever, but this is typically in atmospheres. So here it's pretty much the same expression, except in this expression you're using atmosphere. So it would be partial pressures of the mixture of the gases in your container. So it would be the partial pressures of your products over the partial pressures of your reactants, but it's exactly the same. So it would be the partial pressure of product E raised to the E power, multiplied by the partial pressure of F raised to the F power, and then so on, G, and so on. And then divided by the pressures of the reactant partial pressures. So here I have A, so it would be divided by the partial pressure of A raised to the little a power, multiplied by the partial pressure of B raised to little b power, and so on. If I had C, it'd be multiplied by the partial pressure of C raised to the C power, and so on. So that's how you write out the expression for your equilibrium constant, either in terms of concentration or pressure. Okay, so I hope that's clear. Next thing I want to talk about is how can I determine what is being favored according to the equilibrium constant that I calculate. Now, if you know the concentrations or if you know the pressures at equilibrium, if you're given that in the problem, you can just plug those in and plug in the coefficients and do the calculation to figure out what the constant is at equilibrium, the equilibrium constant. So if you're given pressures, you can put in the pressures and atmospheres for the products, E and F and G or whatever, and the reactants, A, B, C, and whatever, and then calculate what the constant is. Now, be aware that the equilibrium constant for concentration and the equilibrium constant for pressure, these could be different, and most of the time they are, but they could be the same, but they could be different as well. So watch out for that. Pay attention to what you're calculating. Is it Kc or is it Kp? Now, for the equilibrium constant expression, or for the constant itself, when you calculate it, if your K value is larger than 10 to the 2 or 100, that indicates that that reaction is favoring products at equilibrium. So you're going to have more products than reactants at equilibrium. If your K value is less than 10 to the negative 2 or 1/100th or 0.01, that would indicate that the reaction favors reactants at equilibrium. So you're going to have more reactants at equilibrium than products. If your K value is somewhere in between those two, then neither one is favored. So they're going to be approximately equal to each other. The amount of product is going to be equal to the amount of reactant at equilibrium, approximately. So that's how you can use your K value to determine whether the reaction favors products or reactants. So the next thing I want to talk about is homogeneous reactions versus heterogeneous reactions. Okay, so let's talk about homogeneous equilibrium versus heterogeneous equilibrium. So homogeneous equilibrium refers to the fact that all of the products and reactants are in the same state, and that same state is either gas or it's aqueous, right? But mostly it's usually going to be in all gas. So when you have all of your reactants and products in the gaseous state, then they can all be included in the equilibrium constant expression. However, if they're not all in the same state, then some of them will not be able to be included into that expression. And that's in particular solids and liquids. So if you have something that's a solid or a liquid, that's not going to be included in the equilibrium constant expression that I showed a moment ago. So here's a couple of examples that I want to show to make it clear. So here I have a homogeneous equilibrium, because here homogeneous meaning homo is the same, genius is referring to kind, so same kind. So here it's homogeneous because they're all gas. So everything is gas. So when I write the equilibrium constant expression, I can include all of these, because remember, the equilibrium expression includes anything that can change concentration. So you can change the concentration of a gas, you can change the concentration of something that's dissolved in water, aqueous, but solids and liquids don't really change their concentration. So their concentrations are going to stay constant throughout the reaction. Okay? So the equilibrium constant is only dependent upon those species, those reactants, those products that change in concentration, because that's what the equilibrium constant is. That's what it depends on, right? So it depends on only things that can change concentration. Okay, so for this equation here, I could write the expression, we'll say Kc. Kc is equal to, it's going to be products over reactants. So here I have the product NO, so concentration of NO, and it's raised to the power of 2 because that's the coefficient 2. This is the only product I have, so that's it for the top. And then for the bottom, I have 2 reactants, so it's going to be N2. And since N has the coefficient of 1, it's just a 1 up here. We don't write the 1s. And then multiplied by the concentration of O2 raised to its coefficient, but the coefficient is 1, so there's no 1 there. We don't write 1s. And so this would be the K expression for this homogeneous equilibrium. Again, you could do it in Kp, right? Kp would be pretty much the same thing. So Kp would be equal to the pressure of NO, partial pressure of NO, raised to the power of 2 over partial pressure of N2. So the partial pressure of N2 multiplied by the partial pressure of O2. And so you got similar expressions between those two. Now, for the heterogeneous equilibrium, I have here, notice that they're all in different states, right? So here I have solid, here's gas, here's liquid. So if they're not all gas, or if they're not all the same state, then this is called heterogeneous equilibrium. And if you have a solid or a liquid, you don't include those in your expression, because again, your equilibrium expression is only dependent upon those reactants or products that change their concentration. And that doesn't happen with solids or liquids. So don't include them in the expression. So for this expression, my Kc would be equal to, again, products over reactants. So here I have 4 PCl3 liquid. So the PCl3 liquid is not going to be included because it's a liquid. So, and that's the only product I have. There's no other product. So that means I'm only going to have a 1 up here. So 1. And then I'm going to put my reactants on the bottom. So here I have P4 solid. P4 I'm not going to include because it's a solid. It does not change concentration. So I'm not going to put it down there. So don't put it down there. Here I have gas. Gas is good. Oops. Sorry about that. Gas is good. So if you have anything that's gas or aqueous, aqueous is good too because aqueous is something dissolved in water, and so you can change the concentration of that. Um, but we don't have aqueous here, we just have gas. So I'm going to put the concentration of Cl2, and then since there's a coefficient 6 here, it's going to be raised to the power of 6. So then this is the expression, the equilibrium constant expression for this equilibrium here. Now, I could calculate the K value here if I knew the concentration of Cl2 at equilibrium. If they give that to me, I would just plug this into the expression, take number 1 divided by whatever that value is, raised to the 6th power, calculate that, and I would get my K expression. And then I could use that to determine, is the equilibrium favoring the products or the reactants. Okay, so that is a distinction between your homogeneous equilibrium versus your heterogeneous equilibrium. For the heterogeneous equilibrium, do not include solids or liquids in the expression. Only gases and aqueous substances. Okay, so that's it for heterogeneous equilibrium and homogeneous equilibrium. So now let's talk about the relationship of equilibrium constants to temperature. So stay tuned. Okay, let's talk about the relationship between the equilibrium constant and temperature. So when you increase temperature or decrease temperature, that's going to have an effect on the reaction rates in both the forward and reverse reaction. However, it's going to have more an effect on the endergonic reaction, such that it's going to cause the endergonic reaction to go faster than the exergonic reaction. So that way, one side is going to speed up faster than the other side. So if you see here, we have a couple of scenarios. So either the energy can be released during a reaction, right? Going in the forward direction, you can either produce energy, or in going in the forward direction, you could either absorb energy. And so typically, if you have energy being absorbed in the forward direction, you would call that an endergonic reaction. If you've got energy being released in the forward reaction, we would call that exergonic. But of course, we can always view this in the reverse direction as well, right? So going this way, it's endergonic because you absorb energy in this direction. In this reaction here, products, you got energy on this side, so going in the opposite direction, you're releasing energy. And so this direction would be exergonic, releasing energy. But we normally think of things as exergonic or endergonic in the forward direction. So that's typically what we mean when we're talking about an exergonic reaction or an endergonic reaction. But since it's an equilibrium, it's good to kind of keep in mind that it could be, if it's endergonic in the forward reaction, then it's going to be exergonic in the reverse reaction. So this is going to be interesting, or this is helpful, because if you say increase the temperature or decrease the temperature, that's going to have an effect on both rates, right? So if I increase the temperature, then, for example, in this case here, for the exergonic reaction, since energy is being released, if I increase the temperature, it's going to increase the forward and it's going to increase the reverse reaction. However, it's going to have a greater effect on the endergonic reaction. So here, if I increase the temperature for the first one, it's endergonic in this way. So increasing the temperature is going to cause the reverse reaction to go faster than the reverse reaction is. So it's going to affect the reverse reaction more than it is the forward reaction. So what's that going to do? It's going to shift the equilibrium towards the reactants, right? So more reactants are ending up being formed than products at equilibrium. So you can use this to help your reaction either produce more product or reactant, right? So if you want to produce more product, like say from your reaction, you might change the temperature. You might increase temperature, lower the temperature in order to produce more product to shift that equilibrium towards product. So that's what happens when you change temperature. So in this case, if you have an endergonic reaction in the forward direction, if I increase temperature, it's going to cause the forward reaction to go faster than the exergonic reaction in the reverse reaction. Now, the exergonic reaction in the reverse is going to be increased as well, but not as much as the endergonic forward reaction here. And so overall, what's going to happen is that more products are going to be produced at the new equilibrium. So you're changing the equilibrium constant when you change temperature, because you're causing one reaction to speed up more than the other, right? So that's going to cause a shift towards either products or reactants, depending on which side has the energy on it. So in other words, if the forward reaction is endergonic, the increasing temperature will shift the system towards the products. That means that you're going to increase ratio. So here, remember that the equilibrium constant, simply put, in a very simplistic way, it's concentration of products over concentration of reactants. So if the forward reaction is endergonic and I increase the temperature, this is going to shift the system towards making more product. If I increase the product here, then I've changed the ratio of my constant, therefore I change the constant. If I increase the product, I'm increasing the numerator, and therefore I'm increasing K. So that's what it says here. So if I increase the temperature, let's say my forward reaction is endergonic. So here my forward reaction is endergonic. If I increase the temperature, then that's going to cause a shift towards more product. I'm going to increase product, increasing the ratio of the products to reactants. I'm increasing that ratio and therefore increasing the equilibrium constant. So my constant is going to get bigger. Okay. If the forward reaction is exergonic, so up here, so here the forward reaction is exergonic because I have energy as a product. So what's that going to do? It's going to favor reactants. So increasing the temperature, if I increase the temperature, it's going to shift the system toward the reactants. So remember, endergonic is this way. If I increase the temperature, then, oh, I'm sorry, I'm looking at the wrong one. Endergonic, oops. Sorry about that. So for the endergonic here, if I increase temperature, the endergonic reaction is going to be favored. So this is going to increase more than this. This is going to increase, but not as much as the endergonic reaction in the reverse direction. So since this is going to be increased more than this is, then reactants are going to be favored. If reactants are favored, this is going to decrease the ratio of products to reactants. So here, I'm going to favor reactants. So I'm going to increase the reactants. Reactants are on the bottom. They're on the denominator. So therefore, increasing the denominator is going to cause the ratio here to decrease. If the ratio here decreases, then of course, my equilibrium constant is going to decrease as well. And so that is the effect of temperature on your equilibrium constant. Okay, so I'm going to give you a couple of examples to finish off the video. Okay, here's a couple of examples. So the first one I want to deal with is called the dissociation of water. And so this has a special equilibrium constant called Kw. So this is called the water dissociation constant. It is an equilibrium constant because this is an equilibrium, but because this is a special one, we give it a special name with a W. So it's K with a W. So it's an equilibrium constant for the for water. So this is what happens in pure water. So your liquid water is going to divide and dissociate or ionize into H plus ions and hydroxide ions. And so this is an equilibrium, so the H plus and the OH minus can come back together to form water. But this is an endothermic reaction, so it absorbs energy in the forward reaction. So here is the equilibrium constant expression for this reaction here. You'll notice that water is a liquid, so we're not going to add it to the denominator because we don't put liquids or solids into the expression. So we just have the products. Notice the products are aqueous. Aqueous and gas are fine. They can go into the expression. So we just end up with two products multiplied together. The coefficients are 1, so we have ones here. We don't write the ones. And so Kw is determined by H plus concentration multiplied by the OH minus concentration. And this is equal to 0. This is equal to 1.01 times 10 to the negative 14 at 25 degrees Celsius. Now, what would happen if we increase the temperature? So if we increase the temperature, since this is endergonic this way, it's going to favor this direction going forward. So it's going to favor the products. So as I increase the temperature, more and more product is going to form compared to reactant. And so what's going to happen here? Look at the expression. So if I increase the amount of H plus and OH minus, then both of these are going to increase, which means then your Kw is going to increase. So that's going to be important, especially for pH measurements, right? Because remember, pH is dependent upon the H plus concentration. And if this is pure water, typically at 25 degrees Celsius, the pH of pure water is going to be 7, right? And notice that the pH scale goes from 0 to 14. That's because this is 14. But if you change the pH of the water, or I shouldn't say change the pH of the water, but if you change the temperature of the water, if you increase the temperature, then basically the concentration of these two is going to increase, and your Kw is going to change, and your pH scale is based upon Kw. Change Kw, and your pH scale changes, and then the pH of water, neutral water, is no longer 7, but some other number higher than 7. So that's why we say that pH is neutral at 7. That's only true for pure water at 25 degrees Celsius. Okay. So example number 2, here we have a typical reaction that you might use to form hydrogen gas. So if you're in the industry and you want to produce hydrogen gas, this might be a reaction that you would do. Take carbon monoxide, react it with water vapor in the gaseous form, form carbon dioxide and hydrogen gas. Now, here's the K expression for this reaction here. If you'll notice that energy is on the product side, So that means that it's exergonic going this way, endergonic going this way. So in this case, if I raise the temperature, then the reverse reaction is going to be favored more than the forward reaction. So when I raise the temperature, I'm going to favor the formation of reactants, and the reactants are going to increase at equilibrium. So I'm going to have more reactants at equilibrium, which is down here, sorry. So the denominator is going to increase, and the numerator is going to decrease. So that means that I'm going to decrease my constant here, my equilibrium constant, which means that it's not going to favor products. That's going to be bad. If the product that I want to form is hydrogen, and that's part of my industry, I want to produce hydrogen so we can use hydrogen for other things, right? Then I want to produce more hydrogen. So I don't want to raise the temperature to do that. In this case, I'm going to lower the temperature, because lowering the temperature is going to favor the formation of products. So that means more products are going to form, and then I'm going to form more hydrogen. So these are a couple of examples of how temperature can affect the formation of either product or reactant, depending on whether you have an endergonic reaction or an exergonic reaction. That's it for this video. I hope you enjoyed this video. If you did, then please like the video, share the video with your friends and family, hit that like button over there somewhere. Also, make sure you subscribe to my channel, hit that notification bell. When you do, make sure you click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a topic you want me to cover, put that down below. If you have a particular question or a problem you need help with, put that down below. I would love to help you with that. Thanks for joining me, and have a great day.